this moment on, we enter into the second radioactive phase, that of the consumption of flat deuterium. Thus, at each successive step, the column ejects a dodecahedron or alpha particle while the column is going to be fixed on 2 flat deuteriums. Each flat deuterium then becomes a half dodecahedron. It is then that the energy contained in these planar deuteriums will allow the column to restructure by restoring a new dodecahedral link at each stage while emitting gamma radiation. Accordingly, during this second radioactive phase, the internal column retains its shape and mass while the nuclide loses 2 electrical charge units and 4 mass units each. Since there are 10 flat deuteriums available on uranium-234, this second disintegration phase will be carried out in 5 steps of alpha emission, giving the thorium-230, then the radium-226, then the radon-222, then the polonium-218, and finally lead-214. Similarly, in the second radioactive family, with 8 flat deuteriums available on thorium-228, the second radioactive phase occurs in 4 steps of alpha emission, giving the radium-224, then the radon-220, then the polonium-216, and finally the lead-212. Finally, as there are no flat deuterium vacancies, we come to the third phase of disintegration. It is then that the inner column will seek to make the central bulge lose weight. In a first step, the central blister will eject 6 pentagons that will freeze into a new plain deuterium in the parietal gap. There is then creation of an isotope of bismuth with beta emission, and restructuring of the central core without change of mass, but with the column directed now on 2 different directions. This angle of 120 degrees then makes it possible to balance the nuclide with the parietal planar deuterium in the third equilateral position. Thus, lead-214 gives bismuth-214 as the core passes from the form of decahedral oxygen to that of tetrahedral nitrogen at an angle of 120 degrees. While the lead-212 gives the bismuth-212 with its carbon core, which assumes a boron form. Of course, these isotopes of bismuth do not have a zero spin because of their asymmetry. The thinning of the central nucleus then continues, with the rejection of a new group of 6 pentagons that fill a parietal gap in planar deuterium. There is then a new beta emission with creation of an isotope of polonium without change of mass, but with a straightening of the internal column in a straight chain. Thus, bismuth-214 gives polonium-214 with a tetrahedral carbon core, and bismuth-212 produces polonium-212 with a boron core. We then find the previous situation of consumption of two flat deuteriums with ejection of a dodecahedron, or alpha radiation. Under these conditions, the polonium-214 gives the lead-210 while keeping its carbon core, while the polonium-212 produces the lead-208 in a straight chain with 8 dodecahedrons. As the lead-210 still has a swollen carbon-type core, we return to the previous shrinkage situation by ejection of 6 pentagons, which settle as a planar deuterium in the parietal gap. It is therefore bismuth-210 which has a V-shaped column, focused on a boron core, to balance the parietal planar deuterium. And again, the swollen column rejects 6 other pentagons as a planned deuterium into another vacuum gap to give the polonium-210 with a swollen center on a lithium. And again, this nuclide will emit an alpha particle and consume the 2 residual planar deuteriums to finally produce the 206 straight chain at 7 dodecahedra. It is thus observed that the final term of disintegration of thorium-232 results in an internal column of 8 dodecahedrons, whereas that of uranium-238 gives a column of 7 dodecahedra. These two isotopes of the lead are therefore stable because they are well balanced and symmetric as shown by their null spins. And they no longer have enough energy to eject a dodecahedron or alpha particles. Let us recall that the 2 other stable isotopes of lead, 204 and 207, belong to the morphology of the 5th dodecahedral layer. Note also that bismuth-209 is a quasi-stable nuclide. This is related to its structure of double blocking of its V-shaped internal column with a rather large core, which balances the plain deuterium placed at the top of a triangle. Therefore, this nuclide is not derived from a radioactive decay chain, but was created individually during popcorn synthesis of supernova clouds. Finally, we come to the last form of radioactivity of the heavy elements, that of the explosion. First of all, we see that the uranium-235 has a half-spin, that is to say it has a shape reminiscent of that of hydrogen and helium-3. We have just evoked the straight internal columns with 2 branches, typical of the heavy nuclides of 0 spin and therefore symmetrical. Now, we can design an internal structure with 3 branches, where the 3 ends are inserted into the parietal gaps, with 9 other flat deuterium that complete the count of electrical charges. We then get the following mass count. With a basic skeleton of icosahedral morphology, we still have 180 mass units. And with the 12 parietal gaps occupied by 9 flat deuterium and 3 branch terminals, we arrive at a total of 204. Now, at the level of the internal structure, we have 3 branches of 25 pentagons. These branches are connected to a center of morphology in helium-3, that is to say 9 pentagons. We thus obtain a sum of 93 internal pentagons, and therefore a mass of 31 units. We thus obtain a sum of 93 internal pentagons for the inner structure, and therefore a mass of 31 units. This gives a total mass of 235 units, which corresponds well to this analyzed uranium. This structure is axially symmetrical with all the parietal gaps filled, which explains its long half-life period of more than 700 million years. But this nuclide is asymmetrical with respect to a plane, and it remains sensitive to any effect of imbalance. In fact, it can then turn around like an umbrella. And under these conditions, it is the nuclear wall that will open and destroy itself. It is then the flat deuteriums that will provide enormous energy. Moreover, with the scission of the 3 internal branches, the central link of 9 pentagons will disintegrate and eject mainly 3 neutrons in the neighboring space. And if other uranium-235 nuclides are nearby, the absorption of a neutron will unbalance them and precipitate their explosion. This is what is then called the famous chain reaction that produces the nuclear explosion.